Okay, hello all, welcome back. Okay, so this is the second part of our FM lectures for today. So we stopped in previous part about the analysis of FM signal. So this is where we'll continue our lecture. Okay, so let's analyze our FM signal so that we will, from this analysis, we can know more about the spectrum, bandwidth, and also look at the power performance of our FM signal. Okay, first we assume that our modulating signal VMT is equal to EM cos omega MT. Then we substitute our VMT inside the general equation of our FM signal. So VMT then becomes EM cos omega MT dt. And then based on this identity, we integrate our cos EX dx is equal to 1 over A sin EX. So become sin omega MT divided by omega M. So then our VFM is equal to EC cos omega CT plus KF EM divided by omega M sin omega MT. Okay, this is after integration when we assume our VMT is equal to EM cos omega MT. Okay, so this is the general equation after integration, and let's introduce one parameter known as the maximum frequency deviation. So the maximum frequency deviation is equal to KFEM. Okay, KFEM in rad per second, and modulation index is defined as the ratio of maximum frequency deviation to modulating signal frequency, which is equal to delta omega divided by omega M or delta F divided by FM. Okay, since omega is equal to 2 pi F, then we can just cancel 2 pi on both above and below, so it becomes delta F over FM. So this is the definition of modulation index in FM. So from here, okay, we can simplify that KFEM over omega M is actually the beta. So our VFM becomes EC cos omega CT plus beta sin omega MT. Okay, because delta omega is equal to KFEM. Yeah? So then you can just substitute beta in front of our sin omega MT. Okay, and then we expand the cos omega CT plus beta sin omega MT using identity cos A plus B, where cos A plus B is equal to cos A cos B minus sin A sin B. So then our equation becomes EC cos omega CT cos beta sin omega MT minus EC sin omega CT sin beta sin omega MT. Okay, and then we want to simplify. Okay, for next steps, we substitute this cos beta sin omega MT and sin beta omega MT using trigonometric identities known as the Bessel function. Okay, for this Bessel function, expanded using Fourier series where cos beta sin omega MT is equal to J naught beta plus the sums n even until infinite of 2jn beta cos n omega MT. For sin beta sin omega MT, the summation of odd n's up to infinite for 2jn beta sin n omega MT. So we can substitute this cos beta sin omega MT equal to this Fourier series inside the equation here, and the sin beta sin omega MT equal to this summation inside the here over here sin beta sin omega MT. So based on these two equations, our FM equation then become EC cos omega CT, J naught beta. So this is the cos beta sine omega MT. Yeah. So come here, J naught beta. So this is sine beta sine omega MT from here, yeah, to here, then come here. Okay, so we look at this and we expand it further, multiply with EC cos omega CT. So EC J naught beta times cos omega CT plus 2EC cos omega CT Jn beta cos omega C cos n omega mt. Okay, and then the below part is just minus 2EC Jn beta sin omega CT sin n omega mt. Okay, here we have this cos A cos B and sin A sin B. So we expand it using the trigonometry identity cos A and cos B is equal to half cos A minus B plus half cos A plus B, and sin A sin B is equal to half sin A minus B minus half sin, half cos A minus B minus half cos A plus B, right? Okay, so we have already done use the identities before. It's the same thing. So from here, yeah, then we replace, becomes cos omega C minus n omega mt and cos omega C plus n omega mt. Okay, so for the below part, so the 2 now is cancelled now because we have half, right? Okay, we cancel the 2 here with half. And for the parts below, it's EC Jn beta cos omega C minus n omega mt minus cos omega C plus n omega mt. Okay, so this is for above and below that we solve using the trigonometry identities. Okay, so and then further using Bessel identity where J minus n beta equal to minus 1 to the power of n Jn beta. Okay, we can further simplify this long equation. Okay, so equation becomes here. Yeah, so if you look at this equation here, for J, if we start from minus to positive n, if for odd n value, the lower side band, the lower side band will be negative. Okay, for the even, okay, both upper and lower and upper side band will be positive. Okay, so from this we can simplify. From the long equation here, using this Bessel identity, we can simplify using this. Okay, so when we expand, let's say, okay, first we take 0. Okay, when it's 0, then EC J naught beta cos omega CT. Okay, so when it's minus 1, okay, let's say minus 1. So let's look at this first example. Let me illustrate. Okay, let's see, you want to check from minus 1, 0, and positive 1. Okay. So if our, first, if it's negative 1, then since J negative 1 is equal to negative 1 to the power of 1 J n, right? So this is from the Okay. So this is to the power of n jjn beta. So j minus 1 is then is equal to, since it's odd, becomes negative j1 beta. Okay, this is j1. j1 is just j1 lah. J1. Okay, so if you look, if we take integer from -1 up to +1 for n equal to 0, so it's j0 beta cos omega ct. So this is 0, no sidebands. If it's -1, then we have EC j1 beta, okay, minus this is negative, okay, so cos omega c minus omega mt. Okay, so this account for the j minus 1. For j1, for the positive one, it's this one. Okay, EC j1 beta cos omega c plus omega mt. Okay, so that's why when we have odd, every time we have n odd, then the lower sideband part is has negative signs. This is C3, C1. So this is the important thing that you have to take note. For even, it's the same. Positive sign for both upper and lower. Okay. So it's even, you can see upper and lower, both positive. It's even. Okay, so this is the characteristics of our VFM signals. Okay, from this equation here, you can expand. Okay. Let's look at next slide. Okay, so in terms of spectrum of FM signal, okay, so the number of sidebands. So in our spectrum, of course, we have to know the number of sidebands. Okay, and the number of sideband depend on the modulation index or beta. So here we have to refer to the Bessel table. Okay, so these are the spectrum, examples of spectrum for different beta from 0.25, 2, and 5. You can see that the higher beta will lead to higher number of sidebands and larger bandwidth. Okay, but again, it depends on the FM. Because between sidebands, between this is our FM. Okay. So the gap here is our FM. FM. Between the sidebands of FM. So this is our carrier frequency center. So this is the first sideband, omega C plus omega M. The first sideband is our center, is where our FC is. Second sideband, third sideband, and so on. Okay, so here for a given beta from Bessel table, we will know the number of sidebands and also the amplitudes for each sideband. Okay, let's look. So this is the example of Bessel graph. Okay, again Bessel graph. This is Bessel table. Okay, modulation index, and the this J0 is FC, and this is first sideband, second sideband, and so on. So these are the amplitudes. The amplitude, the normalized amplitude. So the actual amplitude you have to multiply it by EC. Okay, for example, when we have no modulation, M beta equal to 0, J0 is equal to 1. So the amplitude of our FC is EC J0. Okay, which means EC. Okay, if you look at the graph, you need to know how to find the sideband, how many sidebands, and the amplitude for each sideband from both from table and also from graph. Okay, let's look at this graph. Okay, when it's beta is equal to 0, we have only up here the carrier frequency, and the relative amplitude is equal to 1. Okay, for the, let's see another example. Let's see beta equal to 2 or 1. Okay, so we have the carrier, and then this is first sideband, then second sideband, third sideband, fourth one. So, and this is the relative amplitude for each component. So this relative amplitude for carrier frequency, relative amplitude for the first sideband, and so on. So this is how you find the number of sidebands and also the amplitudes for each sideband from Bessel graph. So this is trickier compared to Bessel table, because Bessel table is just straightforward. You can refer to table for a given beta, how many sidebands maximum here, and also the amplitudes, relative amplitudes for each sideband. Okay, so summary from the FM spectrum is that, okay, what we can notice is frequency spectrum for FM consists of carrier component at FC and also sidebands at FC plus minus n FM. N is an integer, number of sidebands is n. And the number of sidebands depend on the modulation index. So when B increases, the magnitude of our carrier signal also decrease. And the amplitude of the frequency spectrum of each of the sidebands and carrier depend on the value of our J and beta. So when B increases, the bandwidth of our modulated signal will increase, and thus bandwidth larger than 2 the FM is expected. Okay, so for large number of sidebands, you can see that for large beta, you can see that you can have very high number of sidebands. So obviously bandwidth will be much larger than 2 FM. Okay, so if you want to calculate bandwidth for the using this Bessel table, it's just 2n FM. Okay, say 2n FM. So n it depends on our table. So that's why it's also called Bessel bandwidth. So this is the actual bandwidth, the actual FM bandwidth. We have also another one. Okay, you have already heard of discussion bandwidth. What is discussion bandwidth? So FM can has very high. It can have very high number of sidebands up to infinite. But from experiments, it is shown that errors when we limit this infinite sideband can be neglected if 98% of the power has been transmitted. Okay, so here the figure is 98% of the power. Okay, so it means that the other frequencies that carry another 2% will be removed using discussant's rule. So based on the Bessel function, 98% of the power has been transmitted if the number of sidebands transmitted equal to 1 plus B. Okay, so if our n is equal to, and beta plus 1, then this means that 98% of signal power has been transmitted. Okay, why 98%? It's from the experiment. It says that the errors can be neglected. Okay, so previously we know that our bandwidth is equal to 2 n FM, and from this experiment says that beta plus 1 is where 98% of the power has been transmitted. So we just for Cousins, Just replace this n with beta plus 1 FM. Okay, that's why we have here beta plus 1. And since beta is equal to delta F divided by Fm, okay, can also use this equation. Okay, 2 delta F plus Fm. Okay, so this is the equation for approximated bandwidth using Cousins. Let's look at our next slide. Okay, so what is narrowband FM? Okay, so narrowband FM is when we have our beta is much less than 1 or it's actually less than 0.2. Okay, very small modulation index. So it's called narrowband FM. So we know from our previous equation. Okay, so this is our previous equation based on the general equation. So this is our wideband, also known as the wideband FM. Okay. So in order to reduce to narrowband FM equation, so how? Remember we have question in previous years question on how to prove right the equation for narrowband FM, basically the derivation. So let's simplify this above equation here. Okay, so theta t will replace beta sin omega mt, so it becomes our FMT is equal to EC cos omega ct cos theta t minus EC sin omega ct sin theta t. Okay, with narrowband FM, since our beta is very small, then theta t is much less than 1, approaching 0. So when for a very small theta t, okay, for very small theta t, so cos will be approximately equal to 1, and sine very small theta t can be approximated to that theta t. So you substitute this inside the equation, then it becomes EC cos omega ct, then the cos theta t becomes 1, so becomes 1, and EC theta t sine omega ct. Okay, from here, this one become theta t, and cos theta t, this one here become 1. So then it becomes EC cos omega ct minus EC beta sine omega mt, since our theta t is equal to beta sine omega mt, sine omega ct. Okay, and then we expand this using trigonometry identity. So it's half cos A minus B minus half cos A plus B, but since you have negative, so inverse, so the low sideband then become negative, the upper sideband positive. Okay, so it's EC cos omega ct minus beta EC over 2 cos omega c omega c minus omega mt plus beta EC over 2 cos omega c plus omega mt. So so this is how we derive equations for narrowband FM. And if you compare our narrowband FM equation with full AM equation, you can notice some similarities. Yeah, like okay, it has how many components? 3. Same, omega c, the lower sideband, omega c minus omega m, omega c plus omega m. So it has 1 carrier component and 2 sideband components. Okay, and equation, the amplitude for sidebands also similar. The modulation index here beta EC over 2, here with AM is M EC over 2. But difference is that the LSB component for narrowband FM, the lower sideband here, has negative sign, as opposite face to the LSB component in full AM. So this is the main difference. So here difference mainly at the face of our lower set band. So instead of here positive, it's -4. So it's opposite, 180 degree. So this is differences between narrowband FM and AM. Okay. Okay. So I'll stop here. Yeah. And then we continue for part 3, discussing power and some questions. Some exercise question examples on FM.